Okay, today I want to look at the region of attack, or at least one version of the region of attack problem. Again, we're launching a projectile at some angle theta, some initial speed v naught on level ground, and we are fixing the launch angle and the launch speed, but I can launch it in any direction azimuthally. So I'm not confined to a plane. I can aim my cannon or howitzer or whatever in whatever direction I want. And the question is, what is the volume of all the possible space that I can hit with the projectile, fixing theta, the launch angle, and fixing v naught, the launch speed, but allowing my azimuthal angle to freely range around? And then I want to ask, what angle of theta maximizes that total volume of attackable region at fixed theta? Let's recall previously we've derived the range equation, tells us how far a projectile will land in terms of the launch angle and launch speed. And we've also derived the area beneath the curve of a projectile. There's a couple different ways of writing it. For compactness, I'll just write it as 1/6 the range squared times the tangent of the launch angle. Now, this very much looks like it should be a calculus problem, and indeed it can be. We certainly could think of this as basically a volume of revolution. I have this area underneath my projectile, and I now want to revolve that area about the vertical axis. So if you want to try working it out that way, maybe using the shell method from Calc 2 would be a convenient way of doing that. I'm actually going to use something a little bit different. I'm going to use a bit of ancient geometry from the Greeks. In particular, I'm going to use Pappus's theorem. Pappus had two geometrical theorems related to areas and volumes of surfaces of revolution. I'm going to be using his volume theorem. And this is sometimes called the Pappus-Goldenus theorem because it was elaborated on with a little more detail in, the 1400s, 1500s later by an Italian scientist. Now, here's the statement of the theorem. If I want to calculate the volume of a revolved area, that will simply be 2 pi times the radius of rotation of the centroid of that object times the area of cross-section itself. We've previously worked out where the centroid of a projectile motion's parabolic trajectory is. We actually don't need that result specifically because we can get it instantly from symmetry. I actually only care about the x-coordinate, not the y-coordinate. But that's what I've labeled as C right here. The centroid of this is effectively the geometrical mean of all of that area underneath the arc. And by symmetry, it has to occur at half the range, at least in the x-coordinate. The y-coordinate is trickier to work out. See an earlier video if you want to see that, but we don't need that here. So here in this formula, we basically have the circumference of a circle that's traced out by the centroid of our object, which in our case, that radius from the centroid to the axis of rotation is exactly r over 2. So we know what that is. The area we've worked out earlier, I know the area underneath this curve. So we can simply apply our formulas directly using the Pappus-Goldenus theorem. Now, I probably want to write this down all in terms of the launch angle, especially since we're going to be asking about what theta maximizes that in a sec. So let's use our formula for r here and clean this up a little bit. Okay, we've written everything out in terms of our angles. Now let's clean it up. Don't forget that tangent is, of course, sine over cosine, so some of this will simplify. Okay, assuming I did everything correctly here, we do get a pretty high power of v naught, a high power of g from the cube, and then 8 over 6 should give us 4/3. Interesting that the 4/3 pi kind of shows up here. And then we've got a sine cubed times another sine from the tangent, cosine cubed, but we miss one of them from the denominator of the tangent. So this is our expression for the volume of this region of revolution. This is the volume of space that we can hit with our projectile launched at a fixed V0 and at a fixed angle theta. So now let's work out what angle maximizes this volume. Okay, so now we have our volume as a function of theta. Let's maximize it. Take the derivative, set to 0. Notice here that we'll need to use the product rule. We could also rewrite, say, cosine in terms of a sine and have only one trig function, but let's just go ahead and use the product rule as is. Setting this whole thing equal to 0, noticing the stuff in the front is just a constant, we'll end up getting a nice little simple relation for theta. We can factor this as much as we want. Notice that the bit out front will only be 0 if theta equals, say, 90 degrees. Well, that makes sense. Firing it straight up gives you 0 volume. That's a minimum. If theta equals 0 degrees, that also makes sense. Firing directly horizontally gives you also 0 volume, so also a minimum. Or when this quantity in parentheses is equal to 0, and that's the non-trivial answer. Let's go ahead and set that equal to 0. After doing a little division and then square rooting, we end up with the result that theta should be the arctangent of the square root of 2. For a numerical value, that's about 54.7 degrees. So this is the angle that will maximize that volume of our region of attack. What's a little bit interesting about this is that it's a little bit less than the 60-degree angle we found that maximized the area underneath the projectile trajectory. So if you're just looking to maximize area, 60 degrees gave you the maximum area. But now we're finding that this arctan of root 2, or about 55 degrees, is what maximizes the volume. So although your area will be a little bit smaller, you gain a little bit extra range in that centroid, sweeping out that long circumference from Pappus's theorem that ends up giving you a slightly overall larger volume at this angle. So there we have it. We found the volume of this region of attack. We found the theta that maximizes that region of attack to be about 54.7 degrees. QED.